So today we'll study stability of bioreactors, which we touched upon it a little bit in the last class, but we'll start afresh today. So if we go to the screen, so this whole process is called stability analysis of bioreactors, by which we test the stability of the bioreactors. Now the method that we use is called the Lap-Notch method of stability analysis of chemical reactors. It was started in 1955 by Billu and Amundsen. And the way to do it, as I said, is to be able to write the unsteady state equation given over here, del C del T equals F, unsteady state equation of the system. Now then first thing we do is actually find the steady state of that. So you see here we find the steady state F CSS comma P equals 0. So that's a steady state. So why do we find the steady state? Because what we want to find is that we want to give small perturbations into the system, and small perturbations are always available in the system, because in a real system you always have noise, as we discussed, and we want to see how the system behaves with respect to these small perturbations. Do the perturbations increase with time, do they decrease with time, or die away? If they decrease with time and die away, then the system is stable. If they stay with time and increase over time, then the system is unstable. Now what we have to do is we have to write everything in a vectorial form over here, as we have written, so that to retain the generality of the process or the analysis, and we write it as ddt of C vector equals F vector, which is a function of C vector, where the mouse is, you can see C vector and P vector. So C vector for the chemostat, as we had discussed in the previous classes, consists of two variables. One is a substrate S and the other one is a cell X. And the P vector is a vector of parameters which consists of the following elements: d, the dilution rate; y, the yield ratio of x over s; ks, the Michaelis kinetic constant; mu max is a maximum growth rate; and s naught is the initial concentration of the substrate. So these are the variables that P consists of. Now x is defined as a deviation from the steady state. Why do we define the deviation from the steady state? Is because we want to study how this deviation would change as you keep, as you change the steady state, as you go away from the steady state. If this deviation is going to increase, then then with time, then the system is unstable. If this deviation x of t is going to decrease with time, then the system is stable. So that is the basic definition. That is what we are aiming towards at all points of time. So x of t, why is it x of t? Because x is deviation is a function of time, and we want to study the dynamics of it as a function of time. So that is written as C vector as a function of time minus the steady state. So what we we realized in the last class is that we have to do a Taylor series expansion. So Ct is written as CSS plus x. Okay. So CSS, we have to do a Taylor series expansion of Ct about the steady state CSS. And so what we do is we take the function f, which is a function of the steady state of Ct. Now Ct is written as the steady state plus the deviation and a function of the parameters. Now if we are to do a scalar Taylor series expansion for a certain scalar g, this is the way we write it: g cs about the steady state. Let's say g cs css plus x is g cs, that's the zeroth order term. Then you have the first order term del g del c evaluated at css. I reminded you the other day that this is not del g del css, but this is del g del c evaluated at css, and then del 2g del c square evaluated as CSS times x square over 2 factorial, plus the higher order terms, which be del 3g del c cubed xs cubed over 3 factorial, and so on. Now for a linear stability analysis, first question is that why do we do a linear stability analysis? We do linear stability analysis because we at this point are not interested to find how the system behaves far away from the equilibrium. Okay, linear stability analysis is valid for systems close to the equilibrium, and we are trying to find out how the system is going to behave close to the equilibrium on the application of a small perturbation or a noise. The reason we are not interested in how the system behaves far away from the equilibrium using a Taylor series expansion is because far away from the equilibrium, the Taylor series expansion is not valid. Why is that? What is that's the question. Is Taylor series expansion valid for all values of x? No. What do you think, Lisa? Is it valid for all values of x? What kind of values of x is it valid for? what do you think? Is it valid for all values of x? Yes, right. It is. Taylor series expansion is valid for all values of x. There is no constraint on x for Taylor series expansion to be valid. But if you want to truncate it, then and then only it's valid for small values of x. You see why? Because if x is large, for example, then as you go to x square, x cubed, x to the power 4, these terms would dominate. So leaving those terms out would be a very stupid thing to do. So x, if you see, look at the series over here. If x is much smaller than 1, then what happens? This term, for example, x square over factorial 2 is very small. The next term, x cubed over factorial 3 is even smaller. X to the power 4 over factorial 4 is even smaller. So you can leave all those terms out. Okay. So that's the point. So if you want Taylor series, if you want to truncate the Taylor series at the first order or the second order, then x has to be small. But otherwise, this is like a mantra you need to remember, because most of the students don't get it right. They all say the Taylor series is valid for small values of x, which is absolutely wrong. Taylor series is valid for all values of x, provided you take into account up to infinite terms, okay, or very large number of terms. Say for example, if you have a large value of x, reasonable large value of say almost close to 1 and 0.9999, and you took into account 200 terms, then Taylor series is fine. It's a pretty good approximation. Fine. So here we are concerned. So what is our concern? Our concern is small values of x. Why is that? Because it's a linear stability analysis we are doing, A. B, we are trying to figure out that how the system behaves in the vicinity of the steady state. We are trying to figure out how the system behaves in the vicinity of the steady state. So if you are trying to figure out how the system behaves in the vicinity of the steady state, what is the deviation from the steady state? X. So therefore x has to be much smaller than what? X has to be much smaller than what? Just saying that it's small doesn't make any sense. Whenever you say something is small, you have to compare it with something else. So x has to be much smaller than CSS. Yeah. So that's my criteria. If I want to truncate it over the after the first order term, that is right here. So GCS plus del G del C, CA evaluated at SS times x, then x has to be much smaller than 1. That's much smaller than CSS. So which is the criteria that we'll take. And we want to do a linear stability analysis, and I'm trying to impress upon you the fact why we're doing a linear stability analysis is because we want to qualitatively understand which direction the system is going to go. See, a linear stability analysis will only give you a good qualitative understanding near the steady state. So we want to figure out that this is a steady state. I have a steady state over here. I perturb the system slightly. So how is the system going to behave when I perturb it just after I give the perturbation? Okay, not too far in time. I mean, in the vicinity of the steady state means not too far away in time, in small times from the time you gave the perturbation, how the system is going to behave. Because the morning shows the day, right? If you give a certain perturbation, you see the system behaves in a certain way, you kind of sort of figure out from that how the system is going to behave on a long term, and I will look at that in great detail. So so this is the scalar. Now what would be the vector form of it? So we want to, for the system, for the reactor, the biostat, the chemostat, you saw that it's a vectorial system, right? It consists of many parameters, 6 or so parameters, and 2 variables, the substrate and the excuse me, and the substrate and the cells. Now what is the problem in this system? Our major problem is that you cannot, it's a coupled system of ODEs. You cannot decouple the system, remember. Okay, if you could decouple, then you can treat them as 2 scalar equations, which you cannot, right? Because look at the substrate equation. Go back and look at the substrate equation. I'll show you if you need to. It's a, yeah, this equation, for example, it is both the substrate equation and the equation for the cell. So look at the equation for the cell. It has x over here, and substrate comes in through mu, right? Similarly, the substrate equation, it has s over here, and the cell comes in through x. So both these equations are coupled, and there is no way to decouple them. If you could decouple these equations, then you can solve individually for these equations using scalar expansion, but there is no way to decouple them. So what we need to do is kind of devise a strategy of how to do the Taylor series expansion for a vectorial system. Okay, I'm not sure if you have done that, but even if you haven't, we'll go through it, and if there are questions, you can stop me if you don't understand anything. So this is a Taylor series expansion. What you see on the screen is a Taylor series expansion for a vectorial system. So f here being a vector, FCSS plus X, and A being a matrix and X again being a vector. So, plus HOT higher order terms which we are ignoring. Fine. Now, let us first look at the orders of these. Okay. So, F is a n cross 1 vector, both F. A is a n cross n and X is a n cross 1 vector of variables. So, as a result, this is of course n cross 1. So, everything is matched out both in the left and right hand side. The n cross 1 thing is kind of matched out, right? Dimensionally, it is consistent. Fine. Okay. Now, what is A composed of? What do you intuit to it? I will show you in a minute, but I want you to intuit. Jacobian of the function. Why is that? Because if you go back here, look at this term. So, this is for a scalar, it is del G del C. So, can you tell me what if F consists of, let me write it here. If F consists of F equals F1 F2, okay. Do you know how to write it this way? So, if you are writing a vector and you do not want to waste your space in the vertical direction, this is how you write F1 F2 transpose. Okay. So, and X is X1 X2 transpose, then my A is going to be what? It is a very simple case, del F1 del X1 del F1 del X2 del F del F2 del X1 del F2 del X2. So, this is my A matrix, and similarly for a n cross 1 n matrix you can write it. So, if A is n cross n, or in other words F is say F1 to Fn transpose and X is X1 to Xn transpose. So, this would be del F1 del X1 up to del Fn del F1 del Fx del Xn, and this direction it will be del Fn del X1, and this direction it will be del Fn del Xn, right? Fine with everybody? So, this is my Jacobian, this is how we define my Jacobian. Okay. Now, I can approximate, as you can see in the screen, I can approximate this as this. Now, you have to tell me what are the assumptions involved in that approximation. Let's go back to the screen here. What is the approximation involved in that from here to here? It's very straightforward. I mean, it's not rocket science. A, the higher order terms are ignored, and then FCSSP is a steady state, so that's 0. So, we just put that over here. So, FCSSP is 0 and this is ignored. So, this is approximately equal to, approximation sign is not for FCSSP, FCSSP is equals 0, but for ignoring because we ignored the higher order term, that is why we give. So, FCSS plus X comma P equals AX, fine. And what was, if you let me remind you, what was FCSS plus X comma P? That was dx dt. So, essentially what we have is dx dt equals AX, is it right? Now, this is what I just said. So, the magnitude of the higher order terms, if this is X is very small, then the magnitude of this is going to be small, the magnitude of the higher order terms is going to be smaller than the first order, right. This is what I explained in the scalar case. So, because higher order x square x cubed, it is obviously going to be larger. So, n over here, the order of the matrices is going to be same as the number of species that is there in the system, fine. If you have two species just as you have in the chemostat, so most of the chemostat equations will be a 2 cross 2 matrix, okay, and which also equals the number of equations in the system. It has to equal the number of equations, because for a system which is has to be complete, the number of equations has to equal, for a well defined system, the number of equations has to equal the number of species, right. Fine. So, is that clear up to this point? Okay. So, next we go to the next step, which is that if x is small, then x bar, this is also something I discussed, x bar is much less than the steady state. The deviation is much less than the steady state. Now, somebody has to tell me that I discussed this just now with respect to the scalar concentration. Now, how does this fit into the vector form? So, let us look at the screen. So, if x bar, just now I discussed that x for a deviation, for this whole thing to be valid, the deviation x has to be much smaller than the steady state concentration, but that was for a scalar, for a single species. Now, what if I have a vector? How do I define this? It could be that the concentration of one is smaller, the other one is not smaller, but how do I define this? How do I satisfy this condition? Each of these is smaller? No, that's not the way we do it. Mathematically, that's not the way we do it. What you're saying is x1 is smaller, much smaller than CSS1, x2, and no. Because it's very hard to, it will be a lot of comparisons involved, and how. So, what is the way we do it? Mathematically, some of you might have taken the advanced math course, so you should know if you had. When you have a vector and you want to compare the magnitudes of vectors, how do you do? What determinant? Vector doesn't have a determinant. What is the determinant of vector? How do you compare magnitudes of vectors? You want to go back to class 12 or what? Just before JEE. How do you define? Yeah, how do you compare magnitudes of vectors? Two vectors I give you three. Each of them say consists of three variables. How do you compare the magnitudes? The two variables, three variables, five variables, whatever. Anything larger than one variable. How do you compare their magnitudes? Norms, yes, by comparing the norms of the vectors. So that's the way to compare. And so there are different kinds of norms. Okay, there are there's a two norm, there's the infinity norm, and so on. So if you have the two norm, for example, it will be x1 square plus x2 square plus x3 square. Let's say if you have 3, square root of that. Okay, then you can have the infinity norm, you can have the absolute norm. What is the absolute norm? AB absolute is B, the absolute values of this. Okay, x1 plus. So any of these norms, the most popular is this one norm. Okay, and this is I believe you know how to calculate the length of a vector. So this is defined as the length of the vector, that norm, and that is the most usual norm that you use to compare two vectors. You can use other forms of norms also, like the absolute norm, for example, the infinite norm, and so on. But typically, what you use is this norm, where you just compare the lengths of those vectors, take the squares of them, and sum them up and take the square root. So if I am to going back to the screen, so if I am to decide whether my x is small, I just compare the length of x as compared to the length of the other vector. Okay. So when I have done that, and when that turns out to be small, then I can make this approximation that dx dt equals ax. Okay, clear? So where aij, that is the elements of the matrix A, are given by, just as I showed, f del f. So this is a Jacobian and given by this. So del aij could be written in the compact form as del fi del cj. Okay, is that clear to everybody? Any question you ask me, please. So this is the compact form of writing aij. Okay, so aij are the elements of the matrix A. Okay, now what I want you to sort of tell me, if not completely, but at least to some extent, what would be the solution of this? If I am allowed to go back to this here. No. What is the solution of this equation? Let's not go that far. Dx dt equals ax. What would be the solution? Let me. Yeah. How do you know that? So this is my equation. Let's say, what is the solution of this? Eigenvector into some constant alpha I times exponential, you mean, minus yeah into eigenvalues into t, yeah, and what sigma of that. Okay. So yeah, so how did you get this? How do you know this? Yeah, see, there is a easy way of doing it, which is very straightforward way. Okay. Now this is the equation, and the solution of this is if x equals x naught at t equals 0. What is the easy way? The easy way is x equals x naught exponential at. Okay. Now you have been taught how to break up at. Okay, if a is given, okay, then any f of a, it could be written as a function of the eigenvectors. Okay, eigenvectors and the eigenvalues, right? You are aware of that. I think it's it's f of lambda, what? F of lambda times the eigenvectors also come in there, and if you use that, you can go back to that. Other option is, let's look at the screen. Other option is, this is the solution. Other option is to actually break down Ax right there when you have the matrix in terms of its eigenvalues and eigenvectors, and then you can decouple the system and solve it in this way. Okay, that's like just decoupling the system. That's one way. Other way is to straight away go and solve this in the matricial form and then convert the matricial form into this form. But whatever it is, this is the final solution that you have to remember this solution. This is a well known solution. So ddt of x equals excuse me, a matrix times x. The solution of that would be x is given as sigma times some constant alpha I times beta I being the eigenfunction times e to the lambda I t. You said minus lambda I t, but that's fine, but that depends only how you define your eigenvalue. If you define your eigenvalue as lambda t, then it's 1, and if you define it as minus lambda t, that's another, but that's all right. So if you defined Ax equals lambda x, then it comes out to be lambda it, fine. That's how it is. And if you define Ax equals minus lambda x, then it's minus lambda it, but typically you define Ax equals lambda x. So let's not confuse it. So given the definition that Ax equals lambda x, then this is your solution. There are two ways of reaching this solution. One is, as I said, to use the eigenvalues and the eigenvectors right away and decouple the system and solve it there. The other one is to not decouple it, use the matricial solution form first, get the matricial solution, and then use the Cayley-Hamilton and other theorems to break up that matrix, say matrix. So exponential, this is something you might want to do in MATLAB or Mathematica. Mathematica is a good thing. So if you give your exponential, if you give a matrix, a 3 by 3 matrix, and you give exponential of that matrix, then Mathematical will immediately spit out what. So you put exponential, so you put a 3 by 3 matrix a, okay, input it, then you say exponential of a, and then Mathematical will immediately spit out what that exponential of a is in terms of just another matrix. You see what I'm saying? So so basically it's like this. So a, let's say, is 2 by 2. So a11, a12, a21, a22. Okay. Now exponential of a would be some other matrix b11, b12, b21, b22, but these are related. These are related through the eigenvalues and the eigenfunctions and eigenvalues of the previous matrix. Okay. Now give you a quick problem. Say a equals simple, a equals a1, 0, 0, a2. What would be my exponential of a? What would be my exponential of a? It doesn't have to be 2 by 2, let's say, whatever. 3 by 3, whatever. Any idea? No? It would be e to the a1, 0, 0, e to the a2. Okay, and this is valid for any value. So if you have a diagonal matrix, okay, then any exponential or anything that you do on that is same as doing it on its individual elements. Is it clear, Lisa? If you have a diagonal matrix, any operation that you do on the matrix is same as doing on the individual elements of the matrix. Fine. So I hope you agree with me on this, and I hope you remember this also. Those of you don't, that the vector this is something that we'll need all the time, that if dx dt equals ax, then x is given by this form alpha I beta I into the lambda I t, where lambda I is are the eigenvalues of the system given as x equals lambda x and beta I are the eigenfunctions. Now, what alpha I is a certain constants. How am I going to define? How am I going to obtain those constants is through defining the initial value. So, if my initial value is given at t equals 0, let us say. So, my solution over here is x t equals sigma alpha I beta I e to the power lambda I t, I going from say 1 to n, then my initial value is given x 0 equals x naught, fine. So, I put my x naught equals sigma I equals going from 1 to n alpha I beta I, right. So, this is how I would define my now my eigenfunctions are known. So, there has to be a unique have to be unique values of alpha I such that this will work out, right. So, if your beta I has 3 elements and each of these 3 directions. So, let us say if you have a 2 by 2 matrix and beta I has 3 elements each of these. So, let us say alpha 1 times beta 1 1 plus alpha 2 times beta 2 1 should equal x naught 1, the first element. Similarly, you will have alpha 1 times beta 1 2 plus alpha 2 times beta 2 2 should equal the second element of this, and you have now 2 unknowns, 2 equations, alpha 1 and alpha 2, 2 unknowns, 2 equations. You can solve for them and get the values, fine. So, you just need to invert. Using the eigenvectors of the transpose of the matrix space. You can solve what? Alpha I. Alpha I is directly equals to x naught into let's say yi is the eigenvector of the transpose. Eigenvectors of the transpose. Okay, let's call it. Let's call okay yi. Yeah. Yeah, that's correct. So, you can do it that way also, but anyhow, this is a system of equations with alpha i's as unknowns and these 2 as knowns. So, you can solve them any which way. Okay. So, the eigenvectors are solved, and so the eigenvectors and eigenvalues, how to solve them. I mean, I don't need to repeat them, but still I will just quickly go through. So, this is the eigenvalues are solved using determinant of a minus lambda I equals 0, and then eigenvectors are obtained by solving a minus lambda I times beta I equals 0, fine. So, these are some basic things you have learned in matrix algebra, but these are things you should be able to do, because when a problem is given to you, you have to be able to actually find the lambda i's and the beta i's, fine. So, and just as I said, the initial condition, just as I showed, is shown by that. So, alpha I depends on the initial condition. So, alpha I times beta I equals x naught, okay. So, there are n, for a n by n non-singular matrix, there are n eigenvalues and n corresponding eigenvectors. So, which means that the system is uniquely defined, okay. If there are n eigenvalues and n eigenvectors, then the system is uniquely defined. If there is less than n eigenvalue, n minus 1 eigenvalue, then what does it imply? If there unique solution is not possible. Solution is possible, but unique solution is not possible, and in other words, the system is ill-defined. It's an ill-defined problem, okay. So, essentially what is happening is that you have n variables, but n minus 1 equations. Like we said, if the system has to be completely defined, then you have n variables and n equations. Now, if you have if the matrix is singular, then what it means is that if the rank, for example, is less than the order, then what it means is that the system is ill defined, or in other words, the number of equations that you have from the system is less than the number of variables. When that happens, what are you supposed to do? You are actually not supposed to fiddle around with the algebra. You are supposed to go back to the model and check if there is something wrong with the model, right. You are missing out an equation in the model. There is no point fiddling around with the algebra or the mathematics of it when the system is non-singular, okay. Now, these eigenvalues, now we come towards the stability, to we are kind of walking towards the stability question. These eigenvalues that you get are complex numbers. Okay, in general they are complex numbers. Then they will have a imaginary part and a real part. For example, here any lambda I, am sorry, this should be lambda I excuse me, is written as ai plus minus bi, bi times I. So, b being the imaginary part and ai being the real part, and now we will look at what the effects of these imaginary and real parts are on the system. So, if my eigenvalues, okay, let us see. So, basically what is happening is that I need to have the solution out here. Yeah. So, what is happening is this is my solution, okay, right. So, let us write lambda I as ai plus bi times t. Okay. Now, what happens is, let me write this over here and then let's see. So, x equals sigma alpha I beta I e to the power, let us write it like this, ai plus bi times I times t. Okay, I going to from 1 to infinity. So, this is our basic thing, and now all our stability results will depend on this. Now, you tell me that if my ai is what are the effects that you think of ai and bi. So, look at this, what we are interested in is how it varies with time, right, how it varies with time. So, what are the two factors that are going to decide how it varies with time? Obviously, ai and bi, fine. Now, let us try and try to discuss what would be the effects of different values of ai and bi. So, ai is the real part, bi is the imaginary part. So, ai is the real and bi is the imaginary part. So, you have to tell me that what could you think could be the effects of these? What? Real part should be negative for all kinds of stability. Okay. Now, the imaginary part may or may not be negative. So, what do you think? If it is negative, fine. If it is not negative, if the imaginary part is not negative, then what will happen? System will be stable, but something else will happen. Right, oscillations. See, what does this imaginary part? You know, e to the power I theta, e to the power I x. What does this imaginary part is composed of? When cos and sine. When you write e to the power I x, what is it composed of? A cos and a sine. So, if the real part, say A is the real part and B is the imaginary part. So, here over here, if A is the real part is negative, then definitely means that the system is stable. Okay. If the real part is positive, then the system is always unstable. If the real part is 0, what is it called? You know what it's called if the real part is 0? No. The system is called neutrally stable, that is just stable. Okay. Slight perturbation from this side, slight increase in A will lead to growth or growth of noise, slight decrease will lead to decay. So, it is called neutrally stable, just stable. Okay. So, those are my explanations on the real part. Now, let us look at the imaginary part bi. So, what do you think are the effects of the imaginary part? If the imaginary part is 0, it means that there are no oscillations in the system. If the imaginary part is non-zero, that is positive or negative, then there could be oscillations in the system. So, what you have to do when you are looking at the total system, you have to couple the effects of the real part and the imaginary part. Okay. So, what we did over here is, let us go to the screen, we have divided it into 5 different parts. So, first case is where the real part is negative and the imaginary part is 0. Okay. The system is completely stable, fine. Next is the real part is positive and the imaginary part is 0, the system is completely unstable. Third is real part is 0, but the imaginary part is non-zero, positive or negative. What it means that there will be oscillations, there will be cos and sine part, as a result of which there will be oscillations and sustained oscillations. Sustained oscillation means that these oscillations are not growing with time or decaying with time, they remain what they are, but there are sustained oscillations. I will show you pictures in a minute and you will appreciate this better. Next is that with a negative real part, you have the imaginary part non-zero, which means that there are going to be oscillations, but these are damped oscillations. So, oscillations are large at the beginning and then they slowly decay. Okay. And the last one is the real part is positive and the imaginary part is non-zero, which means that the oscillations start and then they grow with time. Okay. So, so out of this, how many are stable? A is stable, first case is stable, A, number 1, number 2 unstable, number 3 neutrally stable, number 3 is neutrally stable, just stable, okay. Number 4 stable, number 5 unstable, okay. So, 2 of them stable, 2 of them unstable, 1 of them neutrally stable, okay. Let us look at the pictures now. So, this is the case, first case where the real part is negative and the imaginary part is 0, okay. Second case, real part is positive, imaginary part is 0. So, first case, as you see, x decreases, x is a deviation, right. So, you gave a little perturbation, started with a little deviation at t equals 0, and the perturbation or the deviation decreases with time and goes back to the steady state. So, this is your steady state value, okay. At 0 at the bottom of the axis is your steady state value. What do you see? And you increased it to this extent and it goes back to the steady state value, fine. So, that is why this is a stable node. And then the next one is A is larger than 0 and B is 0. So, you start with a small deviation, let us say whatever the deviation value is, and it grows over time. So, the system is, even if it is very small, you give a large, so that is the difference. For a stable system, you gave a even sort of significant perturbation, and still it goes back to 0. For unstable system, you give a small perturbation and that blows up, and these are the most dangerous ones as far as biochemical reactors or any kind of reactors are concerned. And I think I discussed this, the concepts of hotspots here in this class at one point of time, and this is what it is related to. These systems where you have hotspots, you give them a small perturbation and they grow. And let us look at other things, and I will come back to the hotspot question. This is the case where the vortex point, which is called neutrally stable, where the real part is 0 and the unreal part, the imaginary part, is non-zero, and you have sustained perturbation. So, whatever perturbation you gave remains, it does not go away and does not increase either. Then this is a stable one, it is called the stable focus, stable node with a imaginary part or with a perturbation or with a oscillation. So, you start with an oscillation and you give a perturbation, it starts oscillating and then it decreases, and you have read all of this in the control theory, I believe, that it starts decreasing, but it keeps oscillating, but through the oscillation it goes to 0, it decays, but decays in an oscillating way. And the last one is a unstable focus, which is that you start with a give a little perturbation, it starts to oscillate and the oscillations start to increase. Now, this is the one, coming back to the hotspot question, this is the one that actually is most seen in hotspots, okay. So, there are two possibilities of instability. One is this example, the second one here, where it grows uniformly, and this one where it grows through oscillations. Now, what is seen in most reactors and what we are studying, biochemical reactors, that chemical and biochemical reactors, what happens when the system goes unstable, it goes unstable through this unstable focus. The reason being that typically there is an oscillatory part, and if it's especially this happens when there is a what kind of coordinates do you think this will happen? What kind of systems will happen? In circular or spherical systems, okay, in cylindrical or spherical systems. Why? Because you have the radial direction over here, let us see, in the cylindrical system, and these oscillations happen in theta, okay. So, the hotspot starts to rotate. So, these oscillations will actually lead to rotation of the hotspot. So, you have a hotspot over here, and these are, in practical systems, this is what happens. When you study these systems theoretically, we kind of assume, okay, there is a hotspot over here and there is another hotspot emerging and another hotspot emerging and so on. But in a real system that does not happen. What happens is that these hotspots start to travel, because there is a imaginary wave, there is a cos and sine part of it, and there are oscillations, these hotspots start to travel, and as they travel, they gain in size, and then it leads to a huge hotspot, and then there is a whole explosion, the reactor blows up, and that is how reactor, in industries, for example, all these accidents in the plants that you hear of actually happen this way. So, hotspot means a temperature, a small region in the reactor where the temperature grows suddenly, and then it starts to gather, gather in space. Like, for example, if you started over here and then it goes over here, it becomes like this, it goes over here, it becomes like this. So, this is how a hotspot is generated. A small increase in temperature. Temperature is a major problem. Less than concentration temperature is a major problem. You can have concentration spots also, but concentration hotspots, but temperature hotspots is a major problem because it leads to the reactor blow up. So you start with a small hotspot over here, and because there is if there is no unstable focus, if it's just simply unstable, or in other words the real part, imaginary part is 0, then what happens is that the hotspot grows in one space. So it just stays there and keeps growing, which is bad also, but this is a lot worse. Why is it a lot worse? Because it propagates, it helps in propagation. So it goes to another region in space and spreads it over there. Okay, therefore it is, and if it just increases in one space, you sort of have an idea and you can cool and through cooling and stuff like that, but then this propagates, and as it propagates, it continues to infect other regions through hotspots. Okay, regions where there are no hotspots, it continues to infect those. So therefore the unstable focus, so unstable focus means why? There's a focus of hotspot. So this is my focus of hotspot, and that itself is unstable. So there's a focus, and the focus itself is moving, whereas this is a stable focus. The system is unstable overall, but the focus that is there is not unstable. It's unstable in one place. Is that clear? This mathematics and how it translates to the physics of the problem, and these are very real problems. It's just not something that is of mathematical interest. These are things that happen in the reactor, and you read in the papers here and there every now and then that reactors blow up. And this is the reason why reactors blow up, because you have certain noises or perturbations in the system that lead to, and because why is this? What is the root cause of all of this? Is because of the nonlinearity of the reaction. And as we do a problem, just in the next few minutes, you will see that how the nonlinearity starts to infect the system. So because there are nonlinearities in the system, these hotspots are generated to start with. If it's a completely linear system, nothing like that would ever happen. You have a hotspot, it will go away. You introduce a perturbation. You can try this with a linear system. Introduce a small perturbation to the system, it will be decayed. It will damp out and go away. But with a nonlinear system, you introduce a perturbation to the system, it starts to grow. There is possibility that it grows, and what we are here today trying to understand is under what conditions that will happen. Why are we trying to do that? Because as engineers, we want to predict a priori whether there is a possibility of hotspot or not. You don't want to have the hotspot blow up into an accident, and then so you'll get fired if that happens. So you want to take care of your job, and you want to figure out whether the hotspot is going to happen or not, and that is why we're doing all this analysis. I think some of you might have done similar things. So, so as we said that AI plus BIT is the whole thing. AI plus BI times I is the whole thing. And what is the whole thing? The eigenvalue of the system, right? So what we need to find out is what is the nature of the eigenvalue? Is it positive? Is the real part positive or negative? And is the imaginary part positive or negative? But what is of prime importance for us more than the imaginary part? The imaginary part only leads to oscillation. So what is of prime importance to us is the real part. Whether the real part is positive, negative, or 0. If it's positive, it's unstable. If it's negative, it's stable. And if it's 0, it's neutrally stable. So we want to do that. Now, but we want a little clever, and what we want to do is we don't want to compute all the eigenvalues. Why do we not want to compute the eigenvalues? Is because if you have a system like a 2 by 2 system, for example, or 3 by 3 system, it's still possible to go and compute the eigenvalues. But in industries, you have a network of reactions. You don't have reactions where you just with 3 species, and I showed you the examples of these multiple reactions. What happens is when you start a reactor with 2 or 3 species, a whole plethora, a whole network of reactions emerge, because you can't control. Once you put the things in, you don't have control over the entire system. So you want A going to B going to C, or A reacting with B producing C, but then D and E and F and all will come up, and it will lead to a network of reactions. Now when there is a network of reactions, this matrix A that we are talking of will be a large matrix. Okay, it will not be a 2 by 2 matrix. N is going to be a large number, maybe 10 or 20 or 50. There are, most of the industries, many of the industries, in petroleum industry, for example, the number of N, the value of N is very, very large. It could be 100, 200, 500. So how are we going to find 500 eigenvalues each time? It's very hard. So you don't want to find all the eigenvalues, and that's a lot of work. So what you want is a shortcut to figuring out. So your aim is not to find the eigenvalues. We're not doing a course in applied mathematics over here that our job is to find the eigenvalues. Your aim is to find out whether the reactor is going to remain stable or blow up. And for that, you don't need the eigenvalues, but what you need is the signs of the real part of the eigenvalues, and that is what you're concentrated on. So all we need to do is we need to determine if the real part of the eigenvalue is positive or negative. Okay. Now, so this is your equation for obtaining the eigenvalues, A minus lambda equals 0. Now, this equation for finding the eigenvalues could be written as this, right. So, you can just open this up and write this in this form, fine. Is it clear? If it is a n by n matrix, then your eigenvalue would, in this characteristic equation, this is called the characteristic equation for eigenvalues. The characteristic equation for the eigenvalues will have n n cross, it would be of order n, right. Is it clear? Why? Because is it clear, Lisa? Why, or do you want me to go through that? So, if you have ai11 minus lambda, a22 minus lambda, and so on, say an minus lambda, then what is the order of this? So, lambda to the n, okay, and then the other terms. This is the highest order, and then all the lower order terms will be there. Is it clear completely? Okay. So, when you arrange these terms, you collect terms of lambda to the n and so on, then divide the numerator and everything and get it in the cleanest form possible. This is the characteristic equation you get, where lambda n is given by lambda n plus b1 lambda n minus 1 plus b2 to the lambda n minus 2 and so on, bn minus 1 to the lambda times lambda plus bn. Okay. This is how it is given. Now, all you need to do is find, and what is the criteria called? Do you remember? Huh? Yeah, Routh criterion. This is the Hurwitz criteria, if you remember. So, of finding, there are two different ways of finding what the signs of this would be. So, the Hurwitz criteria states that all this is what we will do, and you can do the Routh criteria also. It's either is fine. That states that all roots of an equation will have negative real roots if one is here b1, the first coefficient here is greater than 0, and what is the other one? Do any of you remember? The determinant of this b1, b3, 1, b2, that is, you go this way, 1, b1, b2, b3, like this, is greater than 0. Okay. Now, if this is an n by n matrix, if it is not a 2 by 2 matrix, then this is how it is 1, b1, b2, b3, b4, b5. You see how it's going? It's going zigzagly like this. So, 1 this direction, then this direction, and so on. Okay, fine. It's going like this. So, if I look here, let's go back to the screen. So, 1 b1, then b2, then b3, then b4, then and so on. Okay, and then you start at b3 again here, and then go on in the same direction. You just move and then go on in the same direction, and then up to bn. So, luckily for our case, for the chemostat case, we have how many components? What will be the order of this matrix? 2. Yeah, it's typically 2 by 2, but it could be 3 by 3 if if it's a multiple substrate, or if it's a inhibitor that is involved, then it could be 3 by 3, but typically it is 2 by 2. Why? Because even if there is a multiple substrate, it's different. Even if there is an inhibitor, what we do, we get rid of the inhibitor out of the problem. So, we come up with a 2 by 2 system. If there are multiple substrates, then yes, if S1 and S2 are 2 substrates, then how many, what would be the order of the equation? 3. So, it will be a 3 by 3. So, either it will be a 2 by 2 or it would be a 3 by 3 matrix for us. So, this matrix is either, if it is a 2 by 2, then this is going to be the form. If it is a 3 by 3, then this is going to be the form of it. Okay. So, let us remember this, and you can also prepare for the 3 by 3. Okay. And I do not think you need the generalized form, but I still gave you the generalized form. So, these two criteria have to be satisfied, and they are joined by the logical AND, which means that both of these criteria have to be satisfied. Okay. So, let us now go and look at the stability of this chemostat. Fine. So, this is the stability analysis that we did, and this is generalized. This is valid for everything. Now, what we are going to do is we are going to try and apply it to the chemostat. So, the first equation for the chemostat is what we had done, remember, dx dt equals dilution rate times x naught minus x plus mu times x. This is mu, the whole thing. Okay. The initial calculations that we will do will assume it to be mu. Why would we assume it to be mu? We won't put the whole thing mu max s over ks plus x. We just assume it to be mu. Why would you do that? We'd assume it to be mu as a function of s, but why would we do that? What is the growth rate of the system? What is it? What is the ideal typical growth rate of the system? It's mu times x. right? What is the growth rate of the system? It's mu times x. So I think there is a basic problem here. So let me go to it. So what is the difference between mu times x and just the concept of mu? What is the fundamental difference? Growth is mu times x. So is the growth rate is what is seen on the screen over here, mu max s x over k plus s. Is that the growth rate at all times? Yes or no? I don't understand you nodding. Right, yeah. So I don't know why you couldn't, we're not. So what is the growth rate? The growth rate is mu times x at all times, but the specific growth rate is not the monod growth kinetics at all times. See, there is a fundamental difference. The growth rate is mu times x at all times. Okay, there is no confusion about that. Then next question comes, what model do I use for this specific growth rate? And I can use different kinds of models for specific growth rate. So as a result, when I'm doing this analysis, I want to do it for mu, so that I can plug in any kind of growth rates at a later time, and the model or the analysis would be still valid. Is it clear? Because I think that's the major thing, that you're not differentiating between the growth rate as a whole and the fact that you're using just a monod growth kinetics. You can use a modified monod growth kinetics, you can use the Malthusian kinetics or different kinds of kinetics. So anyhow, so these are the coupled equations that you have, and so my F1. So I need to define my two functions, right, in order to be able to do all this calculations. So what I need to do first, I need to define my two functions, and then I need to obtain my Jacobian, obtain my A using these two functions, and then I need to look at the eigen values of A, not specifically, but we need to look at it through the characteristic equation. Fine. So first step in this is therefore finding the function. So this is my first function and this is my second function. Okay. Next thing I need to do is find the Jacobian. So why would you work on your copies to find the Jacobian? So these are my F1 and F2. Okay. So I want you to find the A matrix. This is minus mu over y, right? You got a plus. Huh? Minus or plus? Minus here. Okay. And this is minus d. Right? Can it be seen as this? Right? So these are my calculations. We'll stop here and continue with the rest in the next class. So I just to quickly capture back. So f1 and f2 are my functions. These are my Jacobian, and I take the derivatives at each step and get this.